And yeah, other than that, feel free to ask questions at any point. Raise your hand and say, I don't get it. And maybe I'll be able to explain it. All right, cool. So welcome, everybody, to SSD Talks. Tonight, we're talking about Rust, which is a really, really cool programming language built by Mozilla. And you may be wondering, why do we need another talk on another language? Why is there another language? Can't people just suck it up and learn Java or C or something? And that's a reasonable question, but the world has changed a lot since C was originally made and since C++ was made. And we've learned a lot of things, a lot from languages like Ruby and from Node and things like that, that translate well really back into these lower level languages. So Rust is, according to the website, a systems programming language that runs blazingly fast, prevents almost all crashes, and eliminates data races. So I'm done, right? Thank you. But actually, it does a lot of really cool things. This preventing almost all crashes is about the same claim that Haskell makes, and it makes that same claim in a lot of the same ways. It does some really cool things because of that, and eliminates data races. Again, that's something that in other programming languages you can't really avoid, because when you have multiple threads running, there's nothing that built into language requires that your memory is safe. Rust does. So specifically, these are some of the main features of Rust. We'll go through basically all of them except for the minimal runtime, which will just be relatively evident, and the efficient C bindings, because I am not a smart enough man to explain foreign function interfaces in a very well-mannered fashion. So this is a Venn diagram of every good program ever written.
Also, exactly none of the programs written in Java.
Exactly. So those of you who are familiar with object-oriented programming, you would know that there would be one circle on this slide, and they would be traveling around together in this happy monogamous relationship. But we here at Rust are a little less traditional. Anyway, so the data and this functionality stay separate so that at any given point you can understand the data you have, the functionality you have, and there's no like concept of, oh, this data carries with it the weight of all the functionality it has with it. You'll see why this is really cool in a little bit. Data being things like structs that you're familiar with from C, and from, it's also primitives, things like that. Just raw data, don't have any functionality associated. So Rust does not have classes. Rust has traits and structs. Structs are pure data, traits are pure functionality. What happens is if I create a trait such as drawable, which means I could draw this on a screen with some program, then I would have structs that represent the data that represents a circle, or a square, or a triangle. So all of these would have, like, for circle, you'd have like radius. That's all you really need for maybe a position, if you were doing position stuff. Square, side lengths, but one side length for a square. Anyway. So what you have is you would implement drawable on the interface. And so we'll see what that looks like in a sec. So structs in Rust are pretty similar to what you're used to in C. You have your very normal definition over here. But you also have tuple structs, which are basically a way of declaring a type that it is 3 ints in a row, basically, but lets you do some type restrictions with that. So you can declare them pretty easily. Using a let statement, Rust does not have type definitions on the left side unless you want them. They're perfectly optional, and we'll see an example of that later. These i's after the numbers indicate that they're integers. You can do an f or float, things like that. And an important thing to note here is that these are immutable. You cannot change it. I could not come on the next line and say origin equals blah, 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 or origin.x equals blah, blah, blah. They are all immutable, which you might think, wow, well, that sucks. I just lost a lot of functionality. And you did, and it's to keep you safe. You can make them mutable in Rust, and we'll get to that in a second. It's very easy, but by default, you're immutable so that you don't shoot yourself in the foot when you didn't expect to. Also, this print line statement here, covering a lot of basic things in this slide. This print line statement is actually a macro. If you notice, it does not require a type annotation here. Like you do in C, we have like %s. Every other format string you've ever seen has that format. Rust, since it's a macro, is aware of the type at compile time and can figure it out for you, which is super cool. Yes?
Two things. One, the i's are totally unnecessary in this case because you said they're all ints.
Yes, they are. I put them in as an example.
The format for a print line comes from Python. Python uses the same exact format.
Python uses %.
No, it doesn't. You've been doing Python wrong for your entire life.
Sort of. Python has format strings that are native and not. This is different. This is a function that's formatting and printing versus Python has format strings, which.
Well, I know, but I'm saying the format.
Sure.
Syntax.
Okay.
The
Anyway, I get it. Yes. Name instantiation is also an upgrade. In early versions of C, certain versions you cannot name them. They can be out of order. Go team. Oh, also trailing comma is allowed. So traits. We have our struct up here, which is our circle, which is very similar to what we said before, but these are 64-bit floats. X, Y, radius. Now we have trait has area, which means that any struct, that's it.
So why is it now after? I mean, before instead of after? Yeah. Like,
Oh, so this is a type definition. This is a type. F64 is a type, not a.
Oh.
Yeah. So this is a declaration of a struct. So I have my value, my field, and my type. Field type, field type. Yeah. If the F was afterwards, it would be, if I just did 64F, that would literally mean the float that is 64, and that would be invalid. So this trait has area. It means that any struct that has an implementation block for has area will have this method area on it that we can use. So basically, trait has area creates more or less a thing that we can treat as a type. A little different. Anyway, so we implement has area for circle, and we basically can reference our fields that we had, which are self.r, and this is a constant that's built into Rust for pi. So now down here, we have a function for print area that can take in, this is the generic syntax. It's similar to what you've seen in Java and C++, where I take in a type T. That T has to be has to implement has area. So traits aren't types, but they're allowed to be used as type restrictions. Yes?
What's the benefit of the 3-step process?
There's a huge benefit. So if you look at the way Rust, the core standard library is implemented, you can see some of the cool stuff you can do. For example, toJSON. toJSON is a trait that allows things to be converted into JSON. And what they were able to do was take all of the structs and things that were built into the standard library, create an entirely separate package that could, for every struct, have an implement block for a trait they define. So now every struct that existed before is able to gain this functionality without it having to be there in the first place, which is really, really valuable. Like, for example, when you implement an interface in a class, you have to do that at class instantiation, which means that your data, which is embedded in the class, is not general purpose, because I can't add interfaces to it later like you can add traits. Does that more or less make sense? Okay, cool. And yeah, so this is a typed parameter, shape of type T. T has to be a has area, and notice we can dot area if we put it there. It looks a lot like classes, but we know what's up. So enums. Enums are not the enums you're used to, though you can express the same kinds of enums in these. The term really for them is algebraic types, and it's a concept from functional programming. Basically, the idea is that you can have a type that is made up of other types. So, for example, an optional type here can be either some or none. So basically what this lets you do is have definitive types. I could say like my enum shape, square, triangle, circle, and that would be it. And then any of those would be valid of that type. So what we're doing with enum here is using the generics to create a sum, which is a tuple struct from what we saw before, and none. So what this means is you can basically say, okay, I get this optional type back. Now, is there actually a value there or not? And that's important because it keeps you from returning null. Because when you return null in a programming language, null is everything. Like any object of any type can be null, which is a problem. So if I have, for example, my vector equals null is valid, and then if I keep moving and don't null check, I could run into an issue. Rust doesn't allow for that because Rust doesn't have a null. What we did was we created a none type, which literally has no value inside of it. It just exists. And so if I had something that returned a maybe, it would, or optional, it would either be some with some value inside of it or none. Here we have a pattern matching example where we're matching against our value, which is of type show, like we saw before. Well, actually, so we have a type restriction of show, and we're taking in a value which is an optional of type T, which has to be of type show. Yes.
Can you put in traits in for instead of just like types for enums?
No. But what you can do is you can put a trait restriction here, like we do here. See, like T show. So if we want to say like optional showable, for example, then we would have T : show, and then the inside would be the same. Yes.
I was going to say that I think what we were talking about is like when you instantiate the optional, you can actually mention something as a trait, and that'll be like Java style polymorphism.
Yeah.
So that's what you can do. You can have generics.
So we have a pattern matching example here, where we are matching if the value is actually null or none. Sorry, we will print line no value found. Otherwise, if it's sum with an embedded value x, we will print the value x. So we noticed we actually managed to draw the value all the way out with this pattern matching example. And you can do some really crazy stuff with pattern matching, and it saves you a lot of time. We might see some more later. So let's talk about dangling pointers. Dangling pointers are a problem. Dangling pointers are when I created 2 pointers to one piece of memory and freed that memory from one pointer. So what happened was pointer 1 pointed to this block in memory. Pointer 1 represents an address for this block. And then later I said, okay, let's demolish what's at point 1. So pointer 1 goes away, but pointer 2 still points there. And so that memory may or may not still be there, and you'll find out at runtime. And you may not even find out. You might find out, 30 lines later when something else goes wrong. So this is actually a huge problem. And there are ways in C++ such as shared pointer and unique pointer, which have been created to solve this problem. But those are runtime solutions. So they have some problems. Rust saves you from yourself. If you're familiar with this type of example, what's happening here is we are creating a function called GetInt that returns a pointer to an int. The and syntax is very similar to C. It's exactly the same. We created a variable x on the stack and then tried to return a reference to it. X would immediately be freed because it was on the stack. And Rust catches that at compile time and presents this exact error. Error bar value does not live long enough, and it'll point you to the exact line. It's a great error, and it's a simple case, but it'll solve that for even pointers embedded in structs. Anywhere, a pointer can never outlive its data. Guaranteed at compile time. Yes?
So, I lost that. What is borrowed value mean?
We'll get to that in just a sec. Borrowed value, yeah, we'll explain that. Borrowers and lenders. So, a borrower is basically anything that gets a pointer to, a borrower is a pointer to something else that it doesn't own. So if, for example, I take in a pointer to a string for read value and print the first character inside of it, that's an UTF-8 character. Feel free to ask questions and we just return it.
I don't get it.
And for those of you who are familiar with Ruby, we are using Ruby-style block returns here.
So, welcome everybody to SD Talk.
I'm hearing myself. Okay, so basically by not having a semicolon here, we are essentially evaluating that as the value of this function. It's a nice shortcut, and you can do some really handy things with it, like if statements can evaluate to values. Anyway, that's why that's returning, even though we didn't write the word return, which is valid in Rust. So there's a lot of these points, and I'm going to kind of generally go over them. I suggest you read them as I talk. Basically, the idea is I can not mutate anything if it's not a mutable pointer. So if I'm given a pointer to something and it's not an and mute, but just an and, so mute versus and, that means that I can't touch it if it's just and. I can read it, but I can't write to it. I can't write to it if you can't create 2 mutable pointers to the same thing. Once you create a mutable pointer, you cannot create another read-only pointer. There's a lot of weird rules that happen here, but again, they more or less make sense as you're writing, and it's not a big deal. So what's happening here is I'm writing do read hi there, which is passing in a pointer to here, which is trying to read in a value. What's happening here is that we're borrowing a value from a borrowed value. So I'm taking a slice of this string that I don't own. But thankfully, what happens is, so I got a string in I, and I took another string out of it, and I read a value out of it. But what I did not do is return it or make it last longer. So it's okay, right? It goes away before I would go away. Yes?
In the write val function, are you saying basically that you cannot set I equal to something else?
I can in write val because I took in a mutable int.
Well, but I'm trying to figure out what the point of the mute is in that statement.
Okay, so what that mute means that the pointer I got allows me to mutate the value inside of it, to change it. So that's what I'm doing here.
It's more along the lines of it's talking that it's like you got a pointer to a changeable value.
Yes, thank you. Yes, the actual pointer itself is not changeable. The value inside the pointer, value where the pointer points to, is changeable. This is all valid Rust code. If I ever show you code that's broken, I'll put an error below it, and you'll see why it's broken. Assume otherwise that it all works. So lenders, if there's borrowers, you have to have lenders. Lending happens when you give out a pointer. So for example, I created a mutable variable x, and I created a mutable vector of numbers. Just so it's mutable, so I can put things into it. It's useful that way. So I put in a pointer to x. Put another one. That's still valid because, again, these are read-only pointers. As long as they go away before x does, we're fine. And since nums is local to the function, it would be fine if it weren't for this line here. I've passed out read-only pointers and then changed the value, which you can't do. That's not valid in Rust. And I'll tell you, cannot assign because it was borrowed. Borrow of x occurs here, and it points you to the exact line. It would show line numbers here, but there's no lines here, so I thought that was more or less irrelevant for you guys. It's really convenient. It shows you where the error happens, and you can solve it. Lifetimes. Rust has this concept of lifetimes, which is very, very different than what you're used to with the heap in C and most of the languages that have a heap model. But it still uses the heap. It's just compile time guaranteed for some cool things. So a box value is a value on the heap. Basically, all I did was say, let's declare a mutable variable x, which is a struct foo with the inner value f equaling 3. And box means we'll put it on the heap. Simple enough. So if some condition, blah, 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 whatever, we're going to create a reference into the middle of x, which is kind of scary, because what happens if x goes away? Rust won't allow that to happen. We actually return the value there, and we're OK. Rust also notices that, notice before when we had the error on right, because we created a reference, Rust notices that this path ends here, and that changing x down here is perfectly fine. So you don't have to worry about Rust forgetting what's going, or not knowing what's going on, and you being smarter than it, because it can figure that out. That's really cool. The lifetime of y begins and it ends, and actually the lifetime of and x.f begins. But anyway, so lifetime annotations. Sometimes you want to do weird things, and Rust is OK with that. So if you have a point which just looks like that, and we're trying to get x out of it, well, we have this awkward scenario. If I want to get a reference to x out of this point, out of this struct, I'm violating that idea, right? I'm taking in a parameter and I'm reading out a value and returning it. But Rust lets me annotate the lifetimes and say that the thing I'm returning only lasts as long as the thing I took in. So it's similar to generics. I say there's for lifetime r, I take in a borrowed pointer with lifetime r and return a pointer with lifetime r to an f64 value, which means that this variable will never outlive the point that it belongs to, which is super cool. So boxes. Back to that box keyword we saw before. It's important to understand how this works because dealing with things on the heap is very valuable. So basically, we have this function getNums, which will return for any n a certain number of values in a vector. So it's going to return a boxed vector of ints. The box indicates that it is on the heap, and wherever the box goes, so does the memory inside of it. Sort of. The lifetime of it does. So passing this boxed value around does not pass the literal value, which is important. That's the value you get from passing pointers. You don't have to worry about copying memory all the time. So we created a mutable boxed vector inside the function, pushed a bunch of values into it, and returned it. What's really cool about this is we created it in the function and returned it like you would do if you were doing a malloc statement or something in C. You would allocate in the function and return, and we can do this safely. Down here is another example of pattern matching and deconstruction, where what happened was we said, let box nums equal this, which basically what that's doing is it's taking actually nums out of the box. So we're saying we're pattern matching. And so this is box nums equals box vector int. So nums is just the vector int, not in the box anymore. It makes sense. It's a little hard to explain, but intuitively, I guess that makes sense. Yes.
Isn't that already on the heap? So that would mean you just.
No, vec is not on the heap.
I'm pretty sure that vec is on the heap and that there's a separate array, static sized array.
I do not. It
So
might
what
be
you're doing is you're making
internally.
a pointer. It's like making a pointer to a vector in C++.
Possibly.
So you've made an extra pointer
Okay.
there.
The point stands.
Okay.
The individual implementations of how vector works under the hood, I am not entirely sure. Honestly, it could be boxing a value inside of it, but for any complex type like this, you can still box it and pass it out for very, very cheap, the price of the pointer. Rust also supports closures much more nicely than C++. C++ has this habit of making the problems for the compiler your problem. For example, if I need to consume a variable from outside, like I do here, that's fine. Rust figures out what variables I need and puts it in. It just does it. In C++, you have to manually define that. I think that's a waste of time, and I think that's mean of C++. But here we have two different ways of declaring closures. If you notice, this one is very similar to the function syntax from before, where we declare all the types of everything. But you can do it without. Closures can have automatically detected types for parameters and for return values. Functions cannot. That's a design decision. They did that so that you're required to put it so that when you see a function definition, you understand what it does. Languages like Haskell don't require that, but they encourage it. So Rust decided to get rid of this problem of encouraging things and require it. We have this issue, though, if we try to say n equals 5 down here after we created this closure, because remember the concept of borrowing, as soon as I create a closure that closes over a value, that value is borrowed, like if we were passing a pointer into it. It's very, very, very nice. It guarantees that the closure will work the way you intended it to work in the first place. Prox. Prox sound familiar to anyone who's used Ruby before and dealt with the frustration that is blocks and procs and functions and everything like that in Ruby. But they have some very unique properties in Rust that make them incredibly useful. Procs can only be run once. They look a lot like closures when you create them. And they live in the heap, which means that you can pass them around for free. They can live for as long as you want easily without having to be managed. And they do one other really cool thing, which is they pull every value that gets closed into them with them to the heap, which does some really cool things. Versus the pointer before, we borrowed. So we would have a life cycle issue if this closure tried to outlast this variable. That's not the case with these. Error, you can't do that. Can't call it twice. Channels. Rust follows a system similar to Go in terms of communicating between processes. You create channels. These are in the standard library. And basically, they have a sender and a receiver, and they allow you to await messages and send messages in and out of processes. So here, basically, all we're doing is spawning a process that says hello. We receive its message, and then we print it, and then we send back goodbye, and it prints that message for us. Pretty simple, but also super easy compared to doing something like this in C++. This spawn statement is incredibly nice. You can take either a proc or a closure. So, yes.
So let's like explain that magic one.
Oh.
TX1.
Okay. This is deconstruction. Similar to the box thing we saw before. Channel is a tuple type that will actually returns a tuple that contains a sender and a receiver.
All right.
And so we're deconstructing it into two variables at once. So we say the first value becomes tx1, second value becomes rx1. It's a convenient way of pulling values out fast. So Rust learned a lot from Ruby and from Node. Package management is an important part, basically a necessary part of a programming language environment nowadays. C# has NuGet, however well that's caught on. And then there's Ruby gems and NPM for Node. And these basically allow the community to center around packages very easily, allow projects to claim dependencies very easily. We'll see how it kind of also takes some ideas from Go in a little bit. Crates.io is its homepage, and this comes bundled with Rust, or it will as of launch. On some platforms it does, some doesn't at the moment. You declare what you want in a toml file, which is like YAML, but less weird, because it can do less in terms of syntax. It's pretty simple what's going on here. We declare a package and some dependencies. These dependencies are pulling from Git repos, but there are other, you know, there's like a Git define, you can define HTTP, you know, direct polls, things like that. This might remind you a lot of Go, where you can just require a GitHub repo, but it does not have a hard dependency on GitHub as it's actually just a full Git URL. Similar to Ruby Gems, it creates a cargo.lock file, which will, if you're collaborating on a project, ensure that you're all on the same version, even if your your cargo.toml does not specify a specific version. So I installed my dependencies, cargo.lock populates with the specific version that I pulled and ensures anyone who starts working on the same project gets the same version until someone updates and commits. Yay. So to use that crate that we just required, Rust has crates as their minimum. It can be compiled. Crates are the libs, basically, of Rust. So we declare an extern crate color to pull it in. And we are going to use two values from two modules inside color, RGB and 2HSV. Again, this is similar to that destructuring concept of don't write something twice if you don't have to. Basically, now we get access to the things inside of it. Similar to what we saw before when trying to use things from the standard lib. They're just there. It's a good time. Also makes sense. So modules and crates. Crates have modules, and crates are what you compile. Modules are what you use. So here we have a crate that is requiring an external crate called color, declaring a module inside of it, and calling a function inside of itself. If I compiled this, I would get a crate that has this hello module inside of it. Go to. I kind of threw a bajillion things at you right now, ending with package management, because I was hoping that would be a little easier. But yes.
Could you explain crates again?
Okay, crates. So when I compile something in Rust, it's similar to something you could compile into an object file in C. The idea of I can compile this chunk of code, and it can be all interdependent. Anything inside of a crate can rely on anything else inside of a crate, but a crate has to stand alone. So basically, I could have multiple files that constitute a crate, and inside of them, I could have many modules declared, and they could all rely on each other in this incestuous way. But when I compile it, it would create one crate that could be used by other projects. Crates are then imported, and then, well, actually you declare them, and then you import the modules that you desire at any given point.
So it sounds like crates are similar to packages?
Yes, a crate is a package. Though a package in Rust, I believe in Cargo, a package could contain multiple crates if it had optional features and things like that. But yes, you thinking of them as a package is a really good way to think of them. Yes.
You have the next slide. So what does pub do?
Yes, thank you. I totally skipped that. Pub means that this method, print hello, is available outside the module. It's public. Everything else is implicitly private inside of this module. And you can put whatever you want inside of here because Rust is a block-based language. So this is just a block. And you could have let statements, you could have if statements, you could have everything you want in there. You'd be happy. Yes. And so that's why we can call it out here. If this pub was gone, this would throw an error. Because I can't call to a method that I don't have access to. Does that make sense?
Removing pub sounds like a bad idea. What we actually impression is.
Yeah, pub is super important, but it's also explicit. So everything is explicitly public rather than maybe implicitly public, like you are in some other languages where you are not private by default. Again, you'll notice that at no point did we ever have to pass functionality around with data. We could if we wanted by using traits, but otherwise our code is kept very clean and very testable. Questions? Yeah.
What does the exclamation mark do, like on print line and all that stuff?
Yes, this exclamation point, all macros end in an exclamation point in Rust to indicate that you're using a macro so that like you can't trick someone into the fact that you're not using it. The reason print line is a macro, as I explained before, is that it taps into the type values, which are erased on compilation. Type values are not carried with variables. That induces overhead that you don't want in a systems programming language. So it can figure out how to print them because it can figure out their types at compile time, generate the code it needs, and then throw the types away so that it's still safe, but I didn't have to tell it what the types were, and it just did. Yes.
together?
No.
So I know one pain in the butt you can see is unit testing because you're like doing this weird macro ass stuff and there's like a bajillion different frameworks out there. Is there a framework for unit testing Rust?
Yes, there is a built-in unit testing framework for Rust. It uses annotations, which I actually didn't cover, but I can basically show you really quick. So annotations in Rust happen when they're basically like decorators in Rust, but they're a language feature. This is too small, isn't it? So, preferences. Oh, right, it's Sublime. I've been in other languages other editors for too long. Cool. Okay, so let's make this a Rust prompt. Okay, so I can do it with, so if I have my function test something that did not, oh, there it goes. Okay, cool, and then there's like a search true, it's a macro, and then you put in some value. And now Rust has these things for decorators, which look like so. And you could do I believe it's a test, and if you can put some parameter type thing in here, and then it would just, you could run the thing for tests.
You don't need to like you use another library.
No, there's a built-in thing into Rust with the intention that this is pretty simplistic, but it's like unit tests in Ruby, so that you have something that you can fall back on without having to worry about reaching out to external libraries. A bit about using Rust today. There are some still major changes going through. I did my best to represent the language as it is at completion, which is all of that code still worked. But there are some edge cases and some other capabilities that are still getting rounded out. They are officially delimited. Rust knows what they're going to be, and they're checking them off. They're working towards their RC and release very shortly, and it's going to be very exciting to see. Yeah, so I guess that's all I got for you guys. Thank you for your time.